All right, folks, today we're going to be finishing up on chapter 10 with addition elimination reactions, and we'll move on to chapter 11. The last part of the course is sort of a whirlwind through various reactions. I'm not going to have time to do a lot of them, but I'll try to hit the highlights. So I wanted to just mention briefly imine formation and some issues with its kinetics and the pH dependence of imine formation kinetics. We're going to talk about acid catalyzed imine formation. And so this, starting with a ketone or an aldehyde, the first step is attack of the amine on the ketone to give you a tetrahedral intermediate. That looks like this. Now, as to whether the amine can attack directly or whether the carbonyl oxygen needs to be protonated first, that can depend on the nucleophilicity of the amine, and your text gives you some insights into that. But basically, the more basic the amine is, the more reactive the amine is, the more likely it is to be able to attack first. Step 2 is basically proton transfer to get you this carbanolamine, which is basically a hemiacetal, except for you're using an amine instead of an alcohol. The next step is the one that requires acid catalysis. And this is the step in which the proton, the oxygen of the OH group needs to get protonated so that it can leave, and so that electrons on the nitrogen can kick down and kick off that leaving group to get us to the iminium ion. And we're going to talk about whether that catalysis is specific versus general. That is, do you protonate the OH group first, and then in a slow step electrons kick down and the leaving group leaves? Or alternatively, does protonation of the OH group happen concomitantly with it leaving in the same concerted step as the electrons kick down on the nitrogen? And whether that's which of those cases we're looking at will depend on conditions, and especially on pH, which we'll talk about. Finally, you've got deprotonation of the iminium ion to give you the imine product. Now, if we look at the pH dependence of the rate of this reaction, appearance of product, and then we have pH on this axis from more acidic to less acidic. We see a profile like this, sort of a bell-shaped profile, where we have maximum rate at intermediate pH values between 6 and 7. And the question is why? At low pH, most of the amine exists in the protonated ammonium form. So there's too much ammonium and not enough amine. And of course, it's that amine that you need to do the reaction. So at low pH, you'd predict that this would be the rate determining step. At higher pH, you have not enough acid for catalysis of step 3. And that would mean that step 3 at high pH, step 3 becomes rate determining. And at lower pH values, you would expect to see some perhaps specific acid catalysis versus general acid catalysis at higher pH values. And of course, at this intermediate pH, whatever it is, you're going to have sufficient amounts of both your amine and HA to facilitate the reaction. Couple of other things in terms of amine-like chemistry. There's some functional groups that are less common that you ought to be aware of. If you use a hydroxylamine with an acid catalyst, or if you use an alkoxyamine, you end up with, and we'll just be general, we'll say this is OR, you can end up with this oxime, and both of these are generally called oximes, and those can be relatively stable. And some have used oxime formation as a way to label a protein that has a ketone in it. If you make an unnatural amino acid with a ketone in it, you can then conjugate some larger R group to that protein via an oxime linkage. If instead of using hydroxylamine or an alkoxyamine, you use hydrazine, you can generate this linkage, which is called a hydrazone. And you could substitute some R groups here if you wanted to. Okay, so that does it for imine formation, and now we're going to talk about a class of biological reactions that use imines to transfer amino groups. Now it is. So I'm going to show you the conversion of an amino acid into, thanks Jude, you just saved me a whole hour later on of re-recording this, so I'll have to do the first few minutes, but into an alpha keto acid, and then I can show you the reverse as well, alpha amino acid. And we're going to use a cofactor called pyridoxal phosphate. And this is kind of an unusual molecule in the sense that it's an aldehyde, and aldehydes are electrophilic, and often, you know, the whole reason that diabetes is a problem is that glucose is an aldehyde, and having too much aldehyde in your blood can modify amines all over the place. So it's kind of interesting that this is a cofactor, but what happens is you take your amino acid plus pyridoxal phosphate and you make the imine. So I'm not going to push arrows for imine formation, but we're talking about linking this amino group to this aldehyde carbon via an imine linkage. So we can just draw that imine directly. Sorry, this should be positively charged. I'm not showing you the phosphate. Recent takers of biochemistry, am I missing anything important so far? Stereocenters on the amino acid, but who cares, because it's not actually going to become a stereocenter in the end. So you've got this imine. Do you see how all of this is the R group up here? Yeah. Now, that imine double bond between carbon and nitrogen happens to be conjugated to this pyridinium ring, which by virtue of being protonated, oh, I am missing something, aren't I? There's a methyl group there and an OH group, sorry. By virtue of being protonated, this ring is electron deficient, and so it can be viewed as something of an electron sink. All right, so in elimination chemistry, we're used to the idea of when you're beta to an electron deficient carbon or an electron deficient atom, you can do an elimination where a base removes this proton and electrons kick here. This is not a positively charged carbon like in the E1 reaction, but if you look at it, we could, by resonance, I'm just going to push arrows real briefly. Do you see that by resonance, we could move this positive charge up onto that nitrogen? So that nitrogen's electron poor, which means the enzyme with some functional group, which we're not going to worry about, can remove that proton. And that's a very, very simple step. In fact, if you look at what we've done, it doesn't look like we've changed much at all. Just sort of, we've removed a proton, so now our molecule is neutral. But look where the nitrogen carbon double bond is. Do you see that? This carbon, oops, we were using, I think, blue. This carbon used to be the aldehyde carbon, all right? Now it's that one. So we've traded, just by a proton transfer reaction, we've traded bonds that are easy to break. Carbon-nitrogen single bond, difficult. Carbon-nitrogen double bond, not a problem. That's just imine hydrolysis. And so now we can break the nitrogen, the carbon-nitrogen bond for the amino acid just via simple imine hydrolysis. And that releases your now alpha keto acid, and also releases the following molecule, which I believe, I could get this wrong, is called pyridoxylamine. Okay, and then we can take this nitrogen and some new alpha keto acid, if we wanted to, and go back this way to make an amino acid. So this is particularly useful for the amino acids glutamate. So here's glutamate. And you can do this same approach with pyridoxal phosphate. I'm just going to, the above reaction, to convert glutamate into 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Alpha ketoglutarate. And you may recognize this as being an intermediate in what? Distant past? Some biochemistry cycle. What?
Alpha-ketoglutarate and glycolysis, right?
No, but the citric acid cycle or the Krebs cycle in mitochondria. Yep. So, so you can, if you need to, you can convert amino acid into something that can go into the Krebs cycle. These are also used to, this equilibria is also used to transport glutamate from one place to another by trading where, by converting on one side of a membrane, I think in mitochondria converting on one side of the membrane from glutamate to alpha ketoglutarate, then letting, I think, the pyridoxylamine diffuse through a membrane, and then on the other side putting the amine back. I don't know. A lot of different things, but it's kind of cool proton transfer / imine chemistry that gives you the ability to move amino groups around. All right, enough about that.
Is that how glutamate is made as well inside?
Is that how glutamate is made inside the cell? Yeah.
Just do backwards.
Yep. So we're totally good at synthesizing glutamate on our own. You shouldn't, which is why it's not one of the essential amino acids. All right. I think we'll now talk briefly about electrophilic aromatic substitution. From this point on, the reactions that we talk about, it's going to sort of be a hodgepodge, and each one we could sort of spend the rest of the semester talking about what's known there. So we're just going to be giving you the sort of headline highlights of these reactions. The basic scheme of electrophilic aromatic substitution is you have some electrophile and some arene, which I'm representing as benzene. The mechanism is thought to go through an equilibrium step where you generate an intermediate. That intermediate is called a sigma complex. Where you formed a sigma bond between one of the carbons of the arene and the electrophile. Doing so breaks one of the pi bonds in the ring, and so you've got a positive charge in the ring, and then usually in a fast step with some base, you re-aromatize. So if you wanted to, you could use the steady state approximation on the sigma complex to generate a rate law for the appearance of product that looks like this. And you know, I'm not going to derive this for you. It's doing so is just similar to what we've done previously. It depends on the presence of the electrophile, the arene, some base, and then in the denominator you've got K-1, which is the backwards rate. That's downhill from the high energy intermediate, and then you also have the K2B term in the denominator. So if the K, let's see, if K-1 is faster than K2, then you're in a situation where the rate law would look like K1, K2 divided by K-1 times the arene, the electrophile, and the base. Then you would see some dependence upon the base. But as you were taught in introductory OChem, we often don't care about what the base is, and it often doesn't need to be present, or rather you don't need a very strong base the counter ion of your electrophile will do, because you restore aromaticity and go downhill. So mostly K2 times B is going to be much greater than K minus 1. And when that happens, your rate law simplifies to K1 times AR times the concentration of the electrophile. And that's what you would expect if this indeed is the rate determining step. All right. A couple of things to consider about electrophilic aromatic substitutions. There is some thought that a pi complex may precede a sigma complex. And so what am I talking about? Well, we've learned that the face of face of arenes is electron rich. And so if you could imagine your electrophile as a cation or just an electron poor species sitting down on the electron rich face of the arene, and it's sort of a non-covalent interaction. And this sort of highlights one thing that we don't often think about in OChem, but if you do calculations on reactions, you see this pretty quickly. We think of starting materials in a reaction, like you've typically drawn the electrophilic aromatic substitution reaction, not like that, energy diagram sort of like this, where you've got starting materials, you've got the sigma complex here, and you have products. What we've taken for granted, though, is in many cases the starting material is actually some kind of complex that's lower in energy than the starting materials at infinite distance. So you could call this an encounter complex, or maybe in this case it's the pi complex. But basically the two molecules have to find each other, and then the reaction can happen. So one way by which that could occur would be by this pi complex. Right. So people have measured the stability of various sigma complexes using this reaction. So you'll have some group X, and then you can use superacid HBF4, and you can see that it would be really, really easy for something to remove this proton to get it back to BF4 minus. That will place a proton on whatever that carbon is that has the substituent. And so let's see. So I'm going to put whatever the X group is here, and then I'm going to put the relative stability of the sigma complex as assessed by that equilibrium constant. So, okay, for hydrogen it's 1. If X equals methyl, the stability goes up. And this is different than the issue of ortho-meta-para directors. I mean, we've talked about, you learned in introductory OChem about electron donating groups versus withdrawing groups and whether they can stabilize the positive charge in the sigma complex. But this may also have to do with the reactivity of the ring where you have electron donating groups that can make the face of the benzene ring more electron rich. So if I continue to add methyl groups, for example, 1,3-dimethyl, sigma complex stability goes way up by a factor of nearly 1,000, or a little bit more than 1,000. And then the third methyl group increases it further, though perhaps not quite as much. Well, almost. Okay, so that's one way to sort of assess the impact of substitution on the benzene ring on reaction rate. And remember, this was a subtle difference in undergrad, or rather introductory OChem. You had substituents and they would have an effect on the rate of the reaction, and then they would have another effect on the Regio selectivity. And you had some groups that were called activators that made the reaction faster. You had other groups that were called deactivators that made the reaction slower, but sometimes a deactivator would still be an ortho and para director. And so this is why, because those are two separate issues. The issue is how reactive is this starting material? And then the issue of Regio selectivity is how stable is this intermediate? Okay. And maybe because of that, we should, instead of calling this relative stability of the sigma complex, we could just call this the relative equilibrium constant, which could be due either to the reactivity of the starting material or the stability of the products. You can see similar trends actually in rates of the bromination reaction, but I won't bother writing those numbers down because they basically confirm a similar thing. Questions so far? Okay, let's briefly do Regio selectivity of electrophilic aromatic substitution reactions. We'll go through this fairly quickly. We'll try to be a little bit more quantitative than your introductory OChem class would have been. So again, we're going to have some X group here, and then we are going to do electrophilic aromatic substitution, and there's going to be three potential products in terms of Regio selectivity. You've got para substitution, you've got meta substitution, and then you have ortho substitution. Does that all look familiar? You're like, oh my gosh, this is boring. We've done this a gazillion times. All right, so let's learn how effective groups are as, say, ortho versus para, ortho meta versus para directors. And let's see the extent to which there's any selectivity between ortho and para. So we're going to define a fraction to normalize. We want to compare, let's see. We want to compare the situation when x equals h to when x equals other things. The problem with when x equals h is you've got 6 reactive positions that are similar. Whereas if you already have an X substituent there, you've got 1 para position, 2 ortho positions, and 2 meta positions. So to normalize for that, what we're going to do is some factor 0 for substituent R, and for the ortho substitution, this is going to be the rate of forming an ortho product divided by 2, divided by the rate for the corresponding reaction for benzene. And if you're starting with benzene, there is no ortho para meta, it's just mono substitution, and we're going to divide that by 6. And then we would do, a similar thing for meta. For para, it would be the rate of para product formation just divided by 1, and then versus the rate for benzene divided by 6. So this is presuming a situation where you can monitor the formation of these three things independently, which sounds like a bit of an analytical challenge. And so I don't really have the reference for you. The reaction, though it is in your text, the reaction is nitration. So our group is, let's say, methyl, T-butyl, and chloro. And then we're going to write these three fractions for ortho, for meta, and para. For the methyl, it's 38.9. I don't know why I need three significant figures. We probably could just round. Ortho, 45.8 para, and 1.3 meta. All right? And remember, this number reflects the fact that there's twice as many ortho positions as there are para positions. So in terms of the rate of the reaction, this should reflect intrinsic differences in reactivity between ortho and para. And the answer is not much, but the meta is pretty unreactive. For T-butyl, see if you can rationalize this. Makes sense. It's not actually hard. Why are we now biased towards para? Sterics, right? If you were to try to, I mean, okay, I talked myself into it. Let's trash that and let's just do benzene, but let's put a T-butyl group on it, and then let's put a methyl group here and see the space. Oh, it's not in the database, but we can see the space filling model. Any substitution you put there is bumping into that T-butyl group. So sterics have a factor here, play a role. If you use chloro, this is where you're going to see the influence of, because remember, these numbers are reaction rates. So you get relative rates for formation of this gives you the sense of Regio selectivity, but we're going to be able to see chloro's role as a deactivator, but still an ortho-para director. So relative to like toluene or T-butyl benzene, chloro, the rate of ortho substitution is much lower, and it's even way more lower than for the meta substitution, and then it's actually decently fast for the para position. So you've learned in introductory OChem why chloro is an ortho-para director. That has to do with resonance donation of lone pairs in the sigma complex that can stabilize the positive charge. But why do you think para substitution is 5 times faster than ortho substitution?
That position is less electron withdrawing.
Right. Why should it be less electron withdrawing? It's just further, right, from the... If chloro's here, the ortho position is going to be more electron poor than the para position just by proximity. So I like these data because they really do summarize a lot of things that we learn in introductory OChem. Here you see the deactivating effect because the rates across the board are slower for chloro, but you also see the Regio selectivity effect. We can do the, yeah.
The rate of formation for the meta, is it the same formula with that for the ortho?
Right, yes, exactly. I'll just go ahead and write that there because it doesn't take too much time. But yeah, rate of meta formation, because there's 2 meta positions, divided by the rate for just unsubstituted benzene over 6. Yep. So these data have already normalized the rates for statistics, which there's twice as many chances to do meta as there are to do para. For the same reaction, not not worrying about Regio selectivity, but just looking at relative rate of nitration. Here are some data for if proton is 1, then OH is 1,000 times more. Methyl, as you've seen, is maybe about 25 times more than proton. Chloro is 0.05 or 0.33, and again, these data do not separate out the Regio isomers, and then if you put nitro there, the subsequent nitro subsequent nitration is way, way, way slower. So this follows your intuition for electron donating groups versus withdrawing groups. A lot of people connect this to the Hammett parameter, the sigma Hammett parameter, which describes how well a group is at electron donating versus withdrawing. Yeah. You have to be somewhat careful at interpreting these results and applying them to other situations. And what I'll say is that for phenol, the rate of the reaction for electrophilic aromatic substitution is faster. And for benzoic acid, we saw that OH had a fairly large positive sigma value, right? Positive sigma. Oh, shoot. All right, now we're going to have to go back and look at it. Dang it. Let's see, is that chapter? Nope. I'm sorry to get mixed up. Okay, we saw that OH had a fairly large negative sigma value, meaning that it destabilized the benzoate because of its electron donating quality. Sorry to have gotten that mixed up. So we've got this rate of nitration issue that tells it's an electron donating group. We also have the benzoic acid thing. But some people have been tempted to apply this insight to predicting how stable some non-covalent complexes should be. So if you look at cation pi interactions, I'm just gonna, let's say potassium here, between phenol and benzene, we can actually look up those numbers. They're probably in your text, I'm just not sure. Oh right, we were looking at bicarbon blood. Let's search for enable dictation. There it was. Cation pi, oh shoot. All right, let's try that again. Cation pi interactions, phenol, benzene, potassium. Close enough, right?
We know.
Okay. Doherty, blah, blah, blah. Oh, shoot. That's not the one we wanted. Let's see, maybe this one. Okay. We had table 2 was to benzene, but I think they're doing fluorobenzene instead of phenol.
Phenol starts with an F.
Yeah. All right. Maybe this is the one, huh? DFT results.
Diction there spells it as F-I-N-G.
Ah, good. So let's take, oh, what do those numbers even mean? Lowest unsigned deviation, mean absolute error. Oh, well, I want to know what the actual numbers are. The bottom line is electrostatic potential surfaces, phenol and benzene. That'll work. All right, so here's the electrostatic potential surface for benzene. This is with phenol. Red color indicates negative electrostatic potential. Basically, you ask the computer to tell you, along the surface of this arene, how much would a positive charge be attracted? And so red areas are places that are electron rich, blue areas are places that are electron poor. You can see that actually for phenol versus benzene, not a big difference in electrostatic potential. So you wouldn't predict there to be a big difference in cation pi affinity for benzene versus phenol in the gas phase or even in biology, despite what we just saw where the OH group accelerates the nitration reaction and is also an electron donating group. So the concept of electron donating group and activator, that's related to reaction rates and stability of high energy intermediates, whereas cation pi affinity is about electron density in sort of ground state molecules. So it's a separate issue. I just remember Dennis Doherty, who really did a lot with the cation pi interaction, was here several years ago, and he pointed this out with a few examples. All right, so that was kind of an aside. I'm sorry, maybe I should have not done that, but I'm in charge, so I can do what I want, right? Okay, that'll be enough for today. Next time we're going to talk about basically alpha carbon chemistry for ketones, and we'll see how far we get.